Okay, let's unpack this. We are so, deeply conditioned to believe that software costs are manageable, predictable.
They're supposed to be. You use historical data, you forecast.
Right. You pay per user seat, you pay per application instance, or, maybe you pay linearly based on scale, like API requests. It's consumption, but it's foreseeable consumption.
Uh-huh.
But here is the massive, almost existential pivot we're facing now. What happens when the software decides the next step? Autonomously, launching complex actions hundreds or even thousands of times a second.
That is the structural departure we need to grapple with, and it changes. Well, it changes the entire financial architecture of the enterprise.
So we're moving from a world we understand.
Exactly. From deterministic scaling, where we can trace the exact code path and estimate the cost with pretty high confidence, to a world of autonomous, non-deterministic loops.
And what does that mean in practice?
It means a single high-level objective, like investigate this market opportunity, initiates a chain reaction. It's a cascade of reasoning steps, tool interactions, external delegation, and recursive subtasks. The cost profile completely shifts from a simple per-request model to a stochastic per-action model.
Stochastic, that's the key word there, isn't it?
It is.
It means the marginal cost of the agent's next action is now decoupled from the initial human trigger. You click go, but you have no reliable way to know what the total bill will be.
Exactly. And this is where the traditional mindset, a comfortable idea of, we'll worry about optimization and budgeting in the next quarter, becomes catastrophic.
Why catastrophic?
Because that mindset is built on the assumption that software moves slowly enough for human intervention or reconciliation. Agents move too fast.
So the economic risk isn't just an accounting headache anymore, it's a critical system failure mode.
Absolutely. Think of it this way. The primary scaling constraint for autonomous AI is not compute power. We can always buy more compute. The primary constraint is economic risk. If the total cost of an autonomous operation exceeds the measurable business value of the outcome, the system has fundamentally failed. It's an economically irrational system.
Because of the speed.
And because these agents operate with such velocity and autonomy, without real-time technical enforcement, without a hard stop mechanism, a single misconfigured agent can enter an infinite planning loop and burn through an enterprise's entire annual cloud compute budget in a matter of hours.
In hours. That really puts the stakes into perspective. The speed of failure is what makes this so different.
It is.
So the mission for this deep dive is clear. We need to understand how enterprises move from managing these predictable software costs to establishing real-time, autonomous financial control. We need to dissect this new taxonomy of AI costs and map out the specific technical architecture, what you call the economic control plane, required to keep those costs from spiraling.
That's the goal.
Our goal is to understand the constraints that must be bounded before the agent is allowed to act, making cost governance a first-class engineering concern.
We have to embed financial accountability directly into the runtime logic. The system has to self-regulate its spending. Otherwise, the risk is simply too high to deploy these agents widely across the enterprise.
All right, so where do we start? To govern something, you first have to be able to see it.
Exactly. To govern these systems, you must first define exactly what you are paying for, and that requires moving beyond just the surface-level API call count. It is a multidimensional cost landscape where the spend is cumulative, and a lot of it is hidden within the agent's internal operational lifecycle, the parts the end user never ever sees.
Let's start with that internal operation, because I think it's the most deceptively large component of spend. You call this the reasoning tax.
It is. It's all the computational cycles required for the underlying foundation models to process massive contexts, generate complex, multi-step plans, and then constantly evaluate their own progress against the initial goal.
So it's a tax on thinking.
It's a non-negotiable tax on agency, yes. The key difference from traditional software is the token spent on internal monologue and all the intermediate state transitions.
Walk us through that internal monologue. If I ask an agent to, say, draft an email summarizing Q3 performance, how much of the computation is just the agent talking to itself?
It can be disproportionately high. For every 100 tokens the user eventually sees in that final email, the agent might have generated 500 to 1,000 tokens internally.
5 to 10 times as much.
Easily. These are tokens dedicated to things like generating multiple candidate plans, critiquing those plans against safety rules, deciding which tool to call next, formatting the internal state log, and critically, rereading its own long history to maintain coherence.
And all those tokens are pure compute, paid for, but entirely invisible to the outside world.
Completely invisible. That's a massive expense for what is essentially overhead.
And I'm guessing the size of that tax isn't fixed.
No, not at all. The depth and complexity of that reasoning chain correlates directly with the parameter count of the model you're using. So if you default to using the most massive general purpose engine, the most capable, but also the most expensive for every single step, even simple ones,
You're maximizing that steep cost gradient.
you're maximizing the tax.
Yeah.
Specialized, smaller, fine-tuned models can handle the procedural steps far more efficiently, but if the orchestrator is lazy and just calls the big model every time, the tax increases exponentially.
So the first governance challenge is simply optimizing the agent's inner voice, making sure it's not overthinking simple problems with an unnecessarily expensive brain.
Precisely. Now, if we move beyond the agent's internal processes, we hit tool execution and external interaction.
Okay, so this is when the agent actually does something in the real world.
Right. When the agent interacts with the external environment, calling an API, running sandboxed code, accessing a database, that carries economic weight, obviously. But where does the hidden systemic risk appear here?
My first guess would be the agent acting on bad data or making a mistake.
That's definitely a risk. But the financial risk is often simpler, and it's something called redundant spend risk, especially in sophisticated multi-agent architectures.
So when you have multiple agents working together,
Imagine you have a complex goal, say, restructuring an internal document archive. You might spin up 3 specialized agents. Agent A retrieves the relevant document IDs, Agent B formats the metadata, and Agent C executes the final system command.
okay, a little team.
Right. But what if agents B and C both decide they need to verify the document ID using the same external metered API call? Maybe because they failed to properly share the state or didn't recognize that a peer had already completed that task?
You've just doubled the cost of that validation step for no reason.
Exactly. They become financially inefficient colleagues, they don't trust each other, so they double-check everything at your expense.
It's a failure of coordination that immediately translates into budget depletion.
Right. Now, let's pivot to the cost of memory itself. We call this the data movement and the semantic retrieval tax.
This sounds like the cost of constantly checking one's notes.
It is. Agentic systems have to rely heavily on a persistent memory layer, vector indices, long-term logs, episodic memory, just to maintain state across long-running multi-day goals.
Makes sense.
The retrieval tax is the compute required for 2 distinct processes. First, the sophisticated similarity searches within that memory to find relevant context. And second, the re-ranking of those search results to prioritize what gets injected back into the prompt.
That retrieval step is already expensive, I'd imagine. But this leads us to what you call the nonlinear problem, the quadratic expansion. This seems unavoidable if you want your agent to be truly well-informed.
This is perhaps the most critical structural challenge to scaling agentic systems economically. That retrieval tax has a nonlinear consequence.
Also,
As agents try to ground their reasoning by retrieving more documents, say 10 documents instead of 5, the context window, the actual prompt size sent to the model for the next reasoning step expands significantly.
and more context costs more money.
But not linearly. Because of how the attention mechanisms in these large language models function, the computational cost of processing that context does not increase linearly. It increases non-linearly, often quadratically.
So if I double the size of the context window, I don't pay twice as much for the next thought. I might pay 4 times as much.
Or more.
Can you give us an analogy for how dramatically this scales?
Sure. Think of it like this. If you are reading a 50-page legal document, it takes time. But if you are suddenly asked to read 50 new documents while simultaneously holding the previous 50 pages completely active in your mind, the cognitive load...
The computational cost.
Right, it doesn't just double. The interaction between all those data points means the effort needed to check every single data point against every other data point explodes.
So the very act of trying to make the agent smarter by giving it more context actually creates an exponential cost burden on its next inference call.
Which is why the philosophy of more context is always better is a financially dangerous one for agentic AI. It's a constant negotiation between intelligence and expense.
Okay, this is a huge hidden cost. Finally, let's look at operational penalties, starting with verification costs.
Trust is expensive. When agents operate with real-world impact-modifying financial records, writing code, or making system changes, trust requires validation.
You need a checker.
You often deploy a critic agent or an independent verification step to check the primary agent's output against safety, compliance, or logical rules. This is necessary, but every verification step doubles the computational cycles required for that action.
So you pay for the action, and then you pay again to check the action.
You pay for the primary action, say 25 execution credits, and then you pay another 25 credits for the independent verification. It all has to be accounted for.
And then there are the costs of failure itself, which you've noted are threefold.
Right. The first is simple: latency-induced opportunity costs. If an agent gets caught in deep reasoning or prolonged recursive retries in a time-sensitive environment, say optimizing real-time inventory pricing, the economic value of its eventual result might be totally negated by the delay.
The perfect answer delivered too late is worthless.
Economically worthless, yes.
Yeah.
The second is incident and rollback costs. If an agent makes an erroneous system modification and then needs to diagnose the failure and revert the change,
The cleanup.
the compute required for that complex diagnosis, which often involves extensive memory retrieval and sophisticated counterplanning, is often higher than the cost of the original erroneous action. The cleanup is always more complex and costly than the initial small error.
Okay, so if we step back from this first section, we've established that we're paying for the agent's internal monologue, its external checks, its memory retrieval with a quadratic penalty, its safety validation, and its failure cleanup.
It's not traditional IT spend, not by a long shot.
It requires a completely different governing mindset, one that is financially proactive, not reactive.
Absolutely.
We've laid out the danger, the economic sinkholes created by this non-deterministic cost. The obvious next question is, how do we build the architectural bedrock to stand on? That brings us to the three core principles you've outlined, which are necessary to embed financial accountability directly into the runtime logic.
Right, and we have to replace post-facto reporting with pre-allocation and real-time enforcement. The shift is from tell me what you spent to prove you have the funds before you start.
Principle number one, the pre-allocated budget envelope. This sounds like the simplest concept, but in the world of autonomous agents, it's revolutionary.
It is the foundation of economic governance. The rule is absolute. Every autonomous action, whether it's an internal reasoning step or an external tool call, must be preceded by a budget reservation. No step is permitted without proof that the required resources are within the current execution envelope.
Why is this non-negotiable? Why can't we just trust the agent to spend and then deduct the cost like we do with traditional services?
Because of the velocity of the agent and the potential for those runaway loops, traditional software costs deduct predictably. Agentic costs can spike instantly and uncontrollably. If you rely on post-facto deduction, you only identify the overruns after the capital has been spent.
By which point it's too late.
It's way too late. This is why the violation here is so critical. Granting agents blanket API keys or unrestricted access without real-time possession caps. That's like handing your agent a corporate credit card with no limit, no fraud protection, and no ability to freeze it instantly.
So the goal is to give the agent a prepaid fixed-value debit card for each specific task. But how do you enforce this technically without crippling the system speed?
Enforcement has to be technical and mandatory. It requires an architectural choke point, a middle-tier proxy we'll discuss later, the policy evaluation point, that intercepts every single request from the agent. Every single one. Before that request is forwarded to the underlying foundation model or the external tool API, the proxy verifies the remaining balance of an abstract entity we call an execution credit. Only if that credit is reserved and verified is the call permitted to proceed. And yes, this verification step must be highly optimized for latency, otherwise it defeats the purpose of the agent's speed.
That makes the financial constraint itself a form of technical permission. Which leads us to principle number two, proportional autonomy.
This is all about linking the degree of independence we grant the AI directly to the severity of the economic risk it faces. The autonomy level must be directly proportional to the estimated cost and impact of the current task.
So we're not just classifying the agent itself, but the risk profile of every action it takes.
Precisely. If we look at a low-risk task, like summarizing an existing dataset, the cost is minimal, the potential impact of failure is just a bad summary. That agent can be fully autonomous.
But a high-risk action.
No, consider a high-risk action, like executing a financial transaction, modifying critical infrastructure, or generating a proprietary legal contract. Those actions require maximum confidence, high-cost reservations, and likely a human-in-the-loop checkpoint, even if the agent believes its solution is 100% correct.
What's the common violation of this principle that you see?
It's assigning a universal level of autonomy to all agents, regardless of their clearance level or the tools they can access. Treating a simple data ingestion agent the same as a complex code-writing automation agent is a massive governance failure.
So you have to differentiate.
You must differentiate based on what we call the agency risk index.
The agency risk index.
Yeah.
How's that calculated in real time? That sounds complex.
It's a multi-factor calculation. It combines the estimated monetary cost of the proposed action with the potential impact of an error, which is often measured by the required rollback cost or even regulatory exposure. If the proposed actions index exceeds a predefined threshold, say a $500 estimated cost or a level 3 system modification, autonomous privileges are revoked instantly.
And it defaults to a human checkpoint.
The system defaults to a human-in-the-loop checkpoint, forcing the agent to stop and present its plan for supervisory approval before the policy evaluation point will grant the execution credit.
That shifts the paradigm from simple permission control to dynamic financial clearance. Okay, finally, principle number 3, mandatory cost attribution. This sounds like an IT accounting constraint, but you're treating it as a core architectural gate.
It is fundamental for governance because it dictates ownership. The rule is that no execution is permitted without a clear, verifiable attribution path back to a specific business unit, project, and ultimately a measurable outcome.
This is to prevent dark spend, right? The forgotten agent that's quietly draining resources in a corner somewhere.
Yes. Dark spend is the silent killer of AI budgets. Mandatory attribution ensures total transparency and allows for accurate chargeback, ensuring every business unit treats agentic compute as the scarce, valuable resource it is.
And the common violation here.
It's pervasive, using shared service accounts that aggregate spend across multiple unrelated workflows. When the $1 million bill arrives, nobody knows which line of business benefited, making any kind of ROI calculation impossible.
So how do we architecturally force this attribution?
Every single system event, every reasoning step, every tool call, every memory retrieval must include a mandatory metadata header. Think of it as a financial passport containing the unique budgeted and the workflow.
And if it doesn't have that passport?
If an event lacks these required identifiers, the communication bus rejects the event entirely. It is stopped at the source. This ensures that every penny spent can be traced back to the specific business purpose that authorized it.
Okay, so we have the principles: pre-allocated budgets, proportional autonomy, and mandatory attribution. Now we need to see how they are translated into a vendor-neutral technical structure, the economic control plane.
Right. This plan is critical because it decouples the execution of intelligence, the agent's brain, from the enforcement of constraints, the system's wallet. It's the central nervous system for monitoring and gating all financial behavior.
Let's walk through the key architectural components. Where do we start? What's the heart of this system?
The heart is the cost attribution engine. It's the central translator and scorekeeper. It receives raw, highly granular telemetry metrics, token counts, bytes transferred, milliseconds of compute, API response codes from every component.
From everywhere.
From the foundation model, external tools, a vector database, everything. Its job is to use a centralized unit cost registry, which holds the real-time pricing for every resource, to translate those raw metrics into a standardized currency value.
And then it connects that cost to a specific task.
It maps the cost directly back to the specific execution ID and the attributed business unit. It turns activity logs into financial records.
That sounds like a heavy data processing load.
Yeah.
You need to be fast, because this information feeds the gatekeepers. Next up, we have the ledger, the budget, and quota service.
This service is the single, non-negotiable source of truth for budget availability. It maintains the hierarchical ledger of all allocated funds, the enterprise, departmental, and workflow quotas we just discussed.
And it handles the credits.
It's responsible for managing the replenishment and, most importantly, the instantaneous revocation of those execution credits. When the policy evaluation point asks, can this agent afford the next step, this is the only service that can say yes or no.
Then we have the cost-aware orchestrator.
Yeah.
We usually think of the orchestrator as purely focused on task efficiency, but here it adopts a financial mandate.
This is a crucial architectural difference. A cost-aware orchestrator does not just prioritize task completion. It elevates cost to an optimization constraint equal to speed or accuracy.
So it's not just what's the best way, it's what's the most economically rational way.
Exactly. Before running any complex multi-step plan, it evaluates the economic path. selecting the most cost-effective models, tools, and reasoning depth for each sequential step. If Plan A costs $100 and Plan B achieves 95% of the outcome for $20, the orchestrator is programmed to choose Plan B, assuming the risk profile allows.
And the gatekeeper itself, the policy evaluation point, PEP, we need a clear physical analogy for this component.
Think of the PEP as the digital tolling booth, or maybe more dramatically, the bouncer at the door of the model API.
I like that one.
It is the critical enforcement layer. It intercepts every proposed action, every single token generation request, and evaluates that request against real-time budgetary constraints and the organization's machine-readable action rules.
Like Agent X cannot modify database Y after 5 p.m.
Exactly. It is the definitive allow or deny decision point that enforces the budget envelope instantly.
And none of this works without a detailed history for forensics. Tell us about the audit component.
We rely on two things. First, the real-time telemetry pipeline, which is a high-throughput stream capturing the actual cost velocity, the rate of spend. And second, the financial audit store. This is an immutable, append-only database.
Immutable is key.
Absolutely. It records every single economic decision, every credit reservation, every enforcement action block, allow, escalate, and every reconciliation event. If there's a catastrophic overrun or if regulators demand an accounting of actions taken, this store provides the defensible, non-reputable audit trail.
Now, let's bring it to life. Walk us through the step-by-step flow, showing how the economic signal actively gates the agent spend.
The flow has three critical phases. It begins in the planning phase. The orchestrator receives the high-level goal, generates a projected task sequence, and uses a difficulty estimator to project the cost for the entire sequence. It then requests a reservation from the budget service.
Essentially earmarking the funds. It's saying, I plan to spend $50 on this task. Please hold $50 for me.
Precisely. That reservation is vital because it locks down the capital before it's spent. This leads to the gating phase, the moment of intervention.
The bouncer at the door.
This is the zero-tolerance checkpoint. Before the agent executes the instruction, say, calling the model to generate the next reasoning step, the request goes to the policy evaluation point. The PEP checks two things simultaneously. Is the action rule compliant? And critically, is the estimated cost of this specific step covered by the remaining balance of the orchestrator's reservation?
And if it's not?
If the estimated cost exceeds the remaining budget, the action is blocked immediately. This is the financial circuit breaker in action. The agent is told no, mid-thought.
And then what happens?
The orchestrator is then forced into a remediation path. It must either degrade its plan to a cheaper alternative or escalate the request to a human supervisor for manual override.
Okay, so then we move to execution and feedback.
Once the action is allowed, the cost attribution engine captures the actual cost, which might be slightly different from the estimate, and reports it to the budget service, which settles the reservation. Any surplus is released back to the parent budget.
And the feedback loop.
Crucially, the telemetry pipeline monitors cost velocity. If the agent is spending at 10 times the expected rate, the PEP receives a real-time signal and can dynamically revoke the remaining execution credits, pausing the agent before the full reservation is even spent.
So this is a self-correcting, high-speed financial ecosystem overlaid on the compute environment.
That's the idea.
The control layer we just defined can't just be one giant budget ceiling, though.
Yeah.
It has to be thousands of tiny targeted fences that mirror the organizational structure. This speaks to the necessity of hierarchical quota management.
Exactly. We need layered limits to manage financial volatility and enforce accountability at every level. At the very top, you have the enterprise envelopes. These are the non-negotiable hard caps for the entire platform across the fiscal year. These are set by the CFO's office.
Below that, it mirrors the business structure.
Yes, you get departmental quotas, which are the fixed allocations for specific business units, marketing, R&D, operations. This is where the concept of chargeback starts to be tested.
But the true engineering challenge is in the granularity.
That's where you have workflow ceilings, the maximum spend allowed for a single long-running goal, like onboard new vendor X. This prevents one critical project from accidentally starving the budgets of all other projects.
And the final, most granular layer is what prevents those catastrophic runaways from single errors.
Those are the per-action caps. These are strict, non-negotiable limits on the cost of a single reasoning step or tool invocation. This prevents the scenario where a single hallucinated prompt Maybe generating a mass a 10,000-word irrelevant analysis exhausts the entire workflow ceiling in one go.
So if the orchestrator estimates the next reasoning step will cost $5 and the per action cap is $4.
The action is blocked instantly, forcing the agent to simplify its thought process.
Now, let's talk about the currency of autonomy, the dynamic budget lifecycle, using these execution credits. This credit system manages the agent's lifespan in real time.
It does. Autonomy is explicitly managed through the active life cycle of these execution credits. If the PPEP checks the credits and the balance is 0, execution stops. The system is designed for both proactive intervention and rewarded efficiency.
Let's focus on the intervention revocation. When should the system decide an agent is not worth funding anymore?
Revocation occurs when the system detects a stagnation cycle. This is identified by the telemetry pipeline monitoring key metrics, high token velocity,
The agent is thinking rapidly and expensively.
coupled with 0 measurable progress, no successful state transitions, no tool calls, no change in output quality. If progress stalls, the system deems the current path uneconomical, and the remaining execution credits are immediately revoked.
Preventing further waste on futile internal debate. So you're monetizing progress, and replenishment rewards efficiency.
Exactly. If the agent is making measurable progress, evidenced by successful subtask completion or moving its workflow state forward, but runs low on its initial credit assignment, the orchestrator can request a top-up from the parent workflow ceiling.
Which is crucial for long, complex tasks.
It's a crucial mechanism for long-running, iterative tasks. It rewards agents that are efficient enough to justify continued investment, but it ensures that the hard ceiling of the workflow is never breached without human approval.
To manage all this, revocation, chargeback, and replenishment, we need impeccable data. We can't rely on abstract log files. We need what you call the economic event schema.
The schema is the foundation of auditability and financial intelligence. Every single reasoning step must emit a detailed record that goes into the financial audit store. It has to contain specific mandatory fields.
Beyond the basics like agent and budget ID.
Right. Beyond the basic attribution, agented, workflow, and budgeted, we need technical fields like cost type, was this reasoning, memory I/O, or an external tool call, and model used. Was it the cheap execution model or the expensive strategy model?
And the crucial financial details.
We need both the estimated cost and the actual cost, and most importantly, the enforcement decision from the PEP. Was the action allowed, denied, or escalated?
And why is that level of detail non-negotiable?
Because it allows for two things. First, the forensic reconstruction of any delegation chain to pinpoint the exact failure point, and second, the precise calculation of ROI for every autonomous action. If an agent spent $10,000 to achieve a result, you have to know exactly which tool calls and reasoning cycles contributed to that cost.
Now let's address that inevitable gap. The variance between what the orchestrator thought the cost would be and the final infrastructure charge. How do we reconcile estimated versus actual cost variance?
The variance is often high, primarily because the outputs of foundation models are non-deterministic. The orchestrator plans for 300 output tokens, but the model, due to a slight prompt change, generates 600.
So you need a settlement process.
A settlement algorithm runs upon the completion of every subtask to resolve this variance. If the actual cost is significantly higher than the estimated cost, say a 20% or greater deviation, it triggers an estimation drift alert.
Why is that alert so critical? It's just an accounting discrepancy, right?
It's a failure of prediction. This alert is the primary feedback mechanism used to retrain the orchestrator's cost prediction models. If the system is consistently underestimating the cost of complex queries, the underlying cost projection logic is flawed. By capturing this drift, we ensure that the governance system itself has a continuous learning loop, improving its financial grounding and its ability to accurately plan for future spend.
So we're not just controlling spend, we're getting smarter about predicting it.
That's the only way to scale.
Okay, so this gets us to a really interesting point. The goal of the economic control plane is not just to spend frugally, but to spend intelligently.
Exactly. The profound shift here is from simply restricting consumption to maximizing utility per dollar spent. This is the core function of cost-utility-based routing.
So the orchestrator becomes the economist of the system, not just the task manager. Instead of just picking the easiest path, it picks the most cost-effective path.
Right. We employ multi-tier model selection. We have to categorize the agent's internal tasks, high-level strategy tasks, complex planning, abstract reasoning, creative generation. Those are routed to the large, high-parameter foundation models.
Expensive ones.
Expensive, but they offer the necessary cognitive power. But the procedural tasks shouldn't be wasted on that expensive compute.
Absolutely not. Procedural or execution tasks, like simply extracting a date from a document, formatting data for an API, or performing a basic classification, should be routed somewhere else.
They're routed to specialized, smaller, highly optimized models. These are fine-tuned engines that can cost 1/100th of the general-purpose model and often perform the simple task faster and more reliably.
And the orchestrator uses a difficulty estimator to make this routing decision. Tell us more about that. How does it rapidly assess the complexity of a query?
It's usually a lightweight, simple machine learning model that analyzes metrics from the query itself. Token length, presence of ambiguous keywords, required number of tool calls, and historical failure rates for similar tasks. It projects the complexity of the query before routing. High complexity means go to the big model. Low complexity means go to the small model pool.
But what happens if the difficulty estimator gets it wrong and the small, cheap model can't resolve the query?
That's where the escalation algorithm comes in. Simple queries are routed to the small model candidates first. The small model performs an internal confidence check. If its confidence score is below a set threshold, the task is immediately escalated and rerouted to a larger, more powerful, and costlier model for a second attempt. This balances initial cost reduction with necessary reliability.
This entire structure hinges on the agent knowing when to quit. We need economic early stopping heuristics.
Agents must be explicitly programmed with a financial conscience to recognize when a goal has become uneconomical to pursue. The core mechanism is the marginal utility check.
Okay, what's that?
Before the agent initiates each reasoning cycle, it has to perform a quick internal calculation. Does the expected value of the next action, measured by a progress score, exceed its projected cost? If the answer is no, the agent must initiate a graceful stop.
So it's not just about hitting a budget limit, it's about proactively deciding the cost-benefit ratio is no longer worth the marginal effort.
Correct. We also implement degradation paths. If the agent detects that its budget is nearing exhaustion, it should be instructed to switch from its pursuit of perfection to a path of graceful degradation.
So instead of a perfect answer, it gives a good enough answer.
Instead of spending thousands of tokens on a deep, complex search for the perfect answer, it might pivot to providing a high-level summary or a partial result, explicitly noting the limitations. This saves the remaining execution credits and maximizes the return on the now limited investment.
Finally, let's revisit the context window tax, that quadratic cost problem we identified earlier. How do we technically fight that expense using pruning and compression?
We have to aggressively reduce the input token count that goes into the expensive inference calls. We deploy dynamic prompt pruning.
What does that involve?
We use specialized, small, cheap models or dedicated prompt processing functions purely to review the existing history and remove irrelevant, redundant instructions or outdated facts from the prompt before the agent sends it back to the main reasoning engine.
You're paying a tiny model to make the prompt cheaper for the big, expensive model to process. That's financial arbitrage built right into the architecture.
Precisely. And second, context compression. Instead of passing raw, verbose tool outputs, say a 5,000-word block of code or an API response between agents or back into the context window.
Which would be hugely expensive.
Right. The system processes that raw output and summarizes the key insights into highly dense GIST tokens. This process can be incredibly efficient, reducing the effective input token count for the next model call by up to 80%, massively mitigating that nonlinear cost increase. It ensures only relevant information, highly compressed, is costing us computation time.
Okay, we've established the controls, but engineering requires preparing for failure. When these autonomous systems fail, they fail financially and often spectacularly fast. We need to categorize these specific economic failure modes. We need a cost failure mode catalog.
Recognizing the pattern of spend is half the battle. We've identified 4 categories of rapid budget depletion that require specific technical responses.
First, the infinite planning loop. This sounds like the agent getting stuck in a rut.
It is. It's the agent failing to find a valid logical path or conclusion and continuing to repeatedly regenerate the same expensive, verbose plan indefinitely. The detection signal is very clear. Sustain, high token velocity, the agent is thinking furiously with zero environment facing state changes or progress markers. It's an internal treadmill.
Next, the retry storms, often related to external tool failure.
This is a classic misconfiguration failure. The agent repeatedly attempts a failing tool call, say an external storage API, that is timing out without adjusting its parameters or recognizing the underlying error.
And the signal there.
A burst of identical API requests, all registering high latency or immediate error responses. Containment requires a fast circuit breaker implemented at the PIP layer to enforce exponential backoff or immediate termination if the error persists.
Then there are the internal budget drains.
Yeah.
Overvalidation cascades.
This happens in sophisticated systems where you have agents reviewing each other. The primary agent and a critic agent disagree on the quality or correctness of an action, leading to an endless loop of refinement, verification, and re-refinement.
How do you spot that?
We detect this with a high ratio of verification tokens to action tokens. The containment strategy is to enforce structural limits, limit validation depth to, say, 3 rounds of internal critique, and force escalation to human consensus if the agents cannot quickly reconcile their differences.
And finally, the silent chronic expense. Zombie agents.
These are the abandoned or forgotten agents. They remain active in background processes, continually querying persistent memory, refreshing state logs, or making low-level health checks without a clear goal or assigned workflow ID. They manifest as persistent, low-level spend with no associated project ROI.
So what's the fix?
Containment requires enforcing a strict time to live, a TTL on all agent states, and an automated decommissioning system that purges unused or orphaned identities.
Knowing the catalog of failure modes allows for defined incident response runbooks. Let's look at runbook A, containment of a reasoning loop. What is the immediate technical action when that loop is detected?
If the telemetry pipeline detects the infinite planning loop, pattern high token velocity, zero progress, the action must be instantaneous. The policy evaluation point's immediate response is to inject a special high-priority system stop message directly into the agent's current context and simultaneously revoke all remaining execution credits.
It forces the agent to stop mid-thought. And the remediation. You don't just turn it back on.
No. Remediation involves a platform engineer analyzing the reasoning trace pulled from the financial audit store to identify the ambiguity or contradictory instruction in the original system prompt that caused the infinite loop. The prompt is then updated with explicit technical stopping criteria, and the agent is often restarted with a shadow budget, a monitor-only mode, to verify the fix before being granted full operational credits.
Now, runbook B mitigation of an overdelegation storm. This is when a parent agent spawns too many costly subagents.
Right. If the budget service detects that a single goal has rapidly spawned an excessive number of subagents, for example, exceeding a rate of 5 subagents per minute, the cost-aware orchestrator immediately pauses the creation of any new subagents and freezes the budget of the parent workflow. This prevents the storm from becoming a flood.
And the fix.
Remediation requires the agent owner to review the delegation logic, ensuring that roles are distinct and not overlapping. The preventative measure here is enforcing a hard max delegation depth constraint at the infrastructure layer, preventing unlimited recursive spawning.
The final failsafe is the human element. But even the human safety net must operate within this governance framework.
Absolutely. Emergency overrides must be defined for mission-critical situations, but they are time-bound, generating a high-priority audit event, identifying the person who initiated the override. Crucially, the override does not disable the economic control plane.
So what does it do?
It shifts the system into a manual supervision mode. In this mode, subsequent actions require human-in-the-loop approval before the policy evaluation point will grant execution. The governance rules are suspended for the human to act, but the attribution and audit trail remain fully active.
Okay, so the technical controls are powerful, but they are ineffective if the organization hasn't aligned its financial operations. This governance capability needs to be integrated into the enterprise financial ecosystem. You talk about 4 distinct stages of economic governance maturity.
Right, and organizations typically progress through them sequentially.
Let's start with stage 1, unmanaged.
Stage 1 is the reactionary stage. Costs are reconciled monthly, weeks or months after the fact. There is zero real-time visibility or cost attribution. Runaway agents are only caught when the bill finally arrives, triggering a panic.
And the goal for a company at that stage?
The primary goal for an enterprise in this stage is simply to implement the unified cost schema and the cost attribution engine so they can begin to answer the basic question, what am I paying for?
Then we move to stage 2, managed.
Stage 2 is observability. Real-time telemetry is finally in place, and spend is correctly attributed to specific agents and workflows. They have dashboards and alerts. However, the alerts are manual. A human receives a notification and must manually intervene to shut down the runaway agent or workflow.
So the goal there is automation.
The goal is to implement the automated policy evaluation point gating, moving from human alerts to technical automated enforcement.
Stage 3 is optimized, where the system begins to make intelligent decisions autonomously.
Correct. In Stage 3, the PEP and budget service are fully operational, enforcing runtime budget caps. Critically, the system is now using dynamic model tiering, that cost-utility-based routing, to reduce marginal cost. The goal for this stage is to evolve the orchestrator to fully adopt sophisticated financial planning, ensuring every dollar spent yields maximized value.
And Stage 4, the ultimate goal, autonomous economic alignment.
This is the mature state where the compute economy is truly self-stabilizing. The system dynamically manages resources not just based on fixed quotas, but based on a real-time assessment of return on investment. Agents are capable of autonomously negotiating for compute credits based on the assessed business value of their tasks, leading to a truly self-regulating, financially optimized environment.
To climb those stages, the governance system has to integrate seamlessly with financial controllership. We need to distinguish clearly between showback and chargeback frameworks.
We do. Showback is the tool for education and visibility. The system generates granular, detailed reports for departmental leaders, showing exactly which agents and workflows are driving consumption. It educates them on the true cost structure of their autonomous workforce without affecting their actual budget ledger. It's used for behavior modification and awareness.
Chargeback, though, is where the rubber meets the road, where hard accountability is enforced.
Chargeback is mandatory for Stage 3 and beyond. The cost attribution engine facilitates actual budget transfers, ensuring that business units treat agentic compute as a scarce resource. This framework is essential for preventing the financial disease known as AI sprawl, where every department builds cheap, unchecked agents because they know the central IT budget is covering the bill. Chargeback forces ownership and responsible deployment.
And finally, the governance system itself must be continuously learning and adapting. How do we monitor for inefficiency within the system?
Through adaptive economic learning. A key indicator is cost drift detection. The system continuously monitors the average unit cost per goal for specific repetitive task types. Say, the average cost to resolve a level 1 customer support ticket. If this unit cost increases over time without a corresponding change in the complexity of the query,
it flags cost drift. And what typically causes that drift?
It often indicates prompt rot, where the instructions to the agent have become inefficient, verbose, or subtly contradictory, forcing the agent to waste tokens. Or it might indicate an underlying unannounced change in the model provider's API or model behavior that the enterprise is now silently paying for. Detecting this drift allows us to intervene and re-optimize the prompt or routing.
So it's not just a one-time setup.
No, and every budget exhaustion incident, rather than being treated as a simple failure, must trigger a formal post-incident economic review. This review determines if the budget was genuinely insufficient for the complexity of the task or if the agent exhibited inefficient behavior. The insights gained are used directly to tune the difficulty estimator and update the policy evaluation action rules, ensuring the controls themselves are improving over time.
And the ultimate organizational alignment requires clearly defined human roles to maintain the system's financial health.
Yes. You have the platform owner, responsible for the technical performance of the economic control plane itself. You have the cost steward, a financial analyst managing the global budget envelopes. And critically, you have the agent owner, the business stakeholder responsible for a specific agent's performance and their assigned workflow budget.
Making them directly accountable.
Directly accountable for any localized runaway incidents and forcing them to review their agent's spending habits.
So what does this all mean? We have moved past simply using autonomous agents. The profound challenge that now defines the field is building an economic control plane that is, paradoxically, as autonomous as the agents it is designed to govern.
It's a huge shift.
Financial control has ceased to be a simple spreadsheet and monthly review exercise. It has become a complex engineering problem solved not with manual intervention, but with proxies, ledgers, real-time intervention points, and a governance architecture that operates at machine speed.
The key takeaways for you as a learner are simple but vital. Agentic costs are nonlinear and non-deterministic, making pre-allocated budget enforcement mandatory, not optional, And your cost attribution needs to be incredibly granular down to the specific reasoning step, so you can differentiate the cost of a memory operation versus an expensive tool call.
And remember that optimization isn't merely about reducing cost. It's about maximizing the cost per successful outcome. Intelligent routing, using cheap models for cheap tasks and escalating when necessary, and early stopping mechanisms are essential for achieving that economic efficiency.
Our final provocative thought builds on that ultimate goal of stage 4, autonomous economic alignment. If the system is fully mature, the agents are dynamically negotiating for compute credits based on their internal calculation of business value. We have to ask ourselves, what happens when the agent's definition of value, defined perhaps by a simple progress metric, differs subtly from the enterprise's true, complex financial philosophy?
That's a fascinating question.
The system may autonomously decide to prioritize low-cost, low-risk outcome over a high-cost, high-value strategy simply because it cannot financially justify the marginal utility of the expensive but potentially breakthrough path.
So managing agency is, therefore, fundamentally managing financial philosophy. We're not just deploying applications.
We are building a self-regulating compute economy that needs guiding principles.